Good morning, ladies and gentlemen. So my name is Jiří Navrátil, come from GESNET, and I would like to invite or welcome you on the session which is called 100G. We would have 3 talks. The first one was the invited talk of Jiří Novotný. Please show me the picture. And maybe you know him from the previous Terena conferences because he visited many of them, and he unexpectedly died in the February this year. So your collaborators and the co-authors of the talk, Viktor Pusch, will have a talk instead of him. So please give the second talk would have, and Viktor Pusch represented the GESNET and the Masaryk University of Brno. The Pavel Škoda again represent the GESNET, and he will have a talk about the cooperation and some interoperability between 100 gig what they tested with the current 10 gig, and Jeroen Kolemej would have the application about the transmission on frequencies. So I would like to ask Viktor Pusch to have a first lesson.
Good morning. Can you hear me? Hello? Okay, thank you. Good morning, everybody. Today I'm going to speak about the implementation of 100G Ethernet in the FPGA. At the beginning, I will briefly introduce 100G Ethernet, what's new, what has remained the same, and also what is the status of 100G technologies, what can we buy, what can not we buy it, what we will never be able to buy for 100G. After that, I will present our work in progress, which is a COMBO-HXT card for the processing of 100G Ethernet. And I will present how we intend to do that in the FPGA. You've heard the set story in the beginning. The second half of this presentation is pretty much work of Mr. Novotný. Okay, the 100G standard, which also defines 40G in the same document, was ratified almost 2 years ago, and it preserves a lot of the principles that were used in 10G and even the older standards, the frame size and format, interframe gaps, management, and so on. And the Ethernet comes in several flavors. There are long-range technologies with the single mode fibers. For 100G, the way it is implemented is that we have 4 colors of light in the same wire, in the same fiber. Each color running at 25 gigabits per second. Also, there's a multi-mode fiber option, which is used for short range, and the parallelization here is done in a matter of parallel fibers within one cable, either for fibers of 10 gigabits per second or 10 fibers each 10 gigabits per second. There is also the backplane and copper flavor of 100G. I'm not going to talk about those. Like I've mentioned, there's a parallelization on physical layers, starting with the lowest layers, which is PMD, PMA. These layers have 10 or 4 lanes. We can see some flavors of that. And at the upper layers, namely the PCS, there are 4 or 20 lines, I will explain how and why we got to the number 20. While many 10G principles have been reused, there are also new principles which force us to re-implement many things. The main differences forcing us to do that is that the data of each frame is split and transmitted simultaneously over all physical lines, which means that if you observe just one of the 10 lines, you will not be able to understand the traffic. The traffic will not be single 10G line. It will be rubbish. Also, a completely new thing are the alignment markers, which are inserted periodically into the stream to disque individual lines because the delay on the optics can be different on each fiber. Also, the scrambling is done before the line distribution, and that's another complication. So therefore, existing 10G physical layer chips, FITers or FICO chips, are not compatible, cannot be used. So we have to re-implement this whole layer. We cannot buy these chips or buy 10 of these chips and connect them somehow together. Okay, this is the stack of layers. The medium access control layer has completely no changes except for the speed. So just the frequency has increased, but everything else remains the same, which is good. Then we have a PCS layer below. The 64 to 60-bit block encoding, again, remains the same. However, the next step is the line distribution, completely new. And the next one is the inserting of alignment markers, also completely new principle in 100G. The PMA layer does multiplexing from the 20 channels or lanes, 20 lines of PCS to the 10 or 4 lines of PMD in case of 100G. In case of 40G, there is no need for multiplexing because PMA and PMD both have 4 lines and the multiplexing is not necessary. This is why we have 20 lines on PMA, because PMD for 100G can have either 4 or 10 physical lines, and therefore we need the number of PMA lines to be divisible by both 4 and 10. The PMD physical media dependent sublayer is just the conversion to the optics, so it's nothing really new in here. The optical transceivers, how they look like, well, they are new, of course, but not in principle. The golden standard for this is the CFP, which is standardized by the most big players in this. And the advantage of these transceivers is that they are almost universal. Almost every flavor of the Ethernet, long range, short range, 40 gig, 100 gig, multi-mode, single mode, almost everything is supported by CFP. However, CFPs are huge. We're building a PCI Express card, and we would be able to fit maybe one, definitely not 2 of them into the slot. So CFP is universal but big. CXP is much smaller. Typical application is short range. It's not that universal. However, it has, let's say, normal size, so it's much more useful. QSFP transceivers, basically, these are for SFP plus within one package. So QSFP is used for 40G, not for 100G. Then there's the second generation of transceivers. These transceivers use 4 lanes in the physical layer. Therefore, each lane has 25 gigabits per second speed. We have retimed or unretimed versions, where the unretimed version is cheaper because it doesn't have electrical retimers within the transceivers. So the quality of signal may be worse. However, it's cheaper, it's greener, and it's intended for short-range communication, maybe data centers, and so on. From those, CFP2 will probably be used for the long distance communication. Okay, here's the bigger overview of the technologies. The optical modules and optical media, of course, are available. However, 25 gigabits per second technologies are expensive. The electrical signaling technologies are also both available. 10Gs are widely used and quite cheap. I will talk a little bit in more detail about 10G for 400 gigabit Ethernet. The 25G technologies are at least announced, and if you have good friends in the vendors, you should be able to get the chips supporting 25G. Therefore, we can conclude that the current generation of 100G is built on 10G technologies in the 10 times parallelization. The second generation will be based on 25G to get higher density and probably lower power consumption, because 4 times 25G usually consumes less than 10 times 10G. I've mentioned the filters, ASIC chips implementing the lower layers of the Ethernet, which were widely used for 10G. However, for 100G they are not available, and they will probably never be. This is because the interface between the filter and the following chip, whatever it is, probably FPGA, would be very wide, probably 520 bits. And doing this on PCB would be really expensive or maybe impossible. So the other option is to do everything within single chip, within FPGA in our case. The current FPGAs, with the exception of the optical interface, can do the whole Ethernet layer stack. They do have enough logic resources today, and they have fast serial transceivers which can form the interface to the optical module, where the signal is just converted from electrical to optical and back and forth. Also, all-in-one chip implementation eliminates the expensive inter-chip communication, and there are also the general advantages of FPGAs, the flexibility, the option of future updates, and also the possibility to do some acceleration of the operations you want to do with the traffic, like filtering, flow processing, CPU load balancing. I will mention that later. COMBO-HXT is our projected card. It's a PCI Express card, full size, with the projected link rate up to 2 times 120 gigabits per second. It consists of 2 cards. The first one, the expensive one, is the interface card. It's the mother card, basic card, which is connected to the PCI Express slot, has the main powerful FPGA, and has connectors to the interface card, which has just the cages for optical transceivers, and can be exchanged if we need some different interface. The main FPGA we will use is Vertex 6 HXT from Xilinx. From the communication point of view, it has 24 fast serial transceivers, GTHs, each capable of over 10 gigabits per second. That's what we need. And it also has 40 slower transceivers, GTX, each capable of 6.5 gigabits per second. Some of those will be used for the implementation of PCI Express communication, because we're using PCI Express generation 2, which has 5 gigabits per second signaling rate. So these will be used for that. The interface card is connected by 2 fast interface connectors, each capable of 120 gigabits per second or more. Also, the main card will have 2 static memories, QDR2+, and a slot for dynamic RAM. Here's the visualization of the card. We can see those white big connectors are the connection to the interface card, and the 2 smaller connectors on the top are connectors which we call low-speed connectors, each of them having more than 10 gigabits per second throughput. They're low speed for us. This is just the flip side of the card. We can see the main FPGA in the center. We can also see the slot for dynamic RAM and the PCI Express connector, of course, and the remaining connector, the white one, which will probably be black after they manufacture it, is the additional PCI Express connector, which doesn't look like PCI Express right now, but if we have some really small piece of PCB connected to this connector, which has the right size and dimensions, it will create additional PCI Express connector right next to the main one, and this whole combination of cards will be connected into 2 PCI Express slots on the main board. So we will have 2 PCI Express devices visible on the bus. The interface cards for 40G, we will reuse existing card for 1G, except we will use not SFP transceivers, which are 1G, but SFP plus, which are 10G. Therefore, this card, equipped with SFP plus transceivers, will implement the PMD layer of 40G Ethernet, and this card is available now. The 100G interface card will have 2 interfaces. We will use CXP because of the size, and this card will implement the PMD layer of 100G Ethernet. We will have additional signal conditioning retimers there because the electrical signal will have to travel a couple of centimeters, and the quality of signal is lost really fast if it's 10G. With the use of the special breakout cable, we should be able to do 6 times 40G or 24 times 10G with this card and the mother card. This is yet to be developed. Here's the block diagram. The main part, of course, is the FPGA, which will implement all the layers, except for PMD, all the layers of the Ethernet, including the management, which has to be there. What we also currently have is a DMA transfer engine, really powerful, to transfer the data to the to the host RAM or from it. Also, we can use some packet processing, filtering, and so on in the FPGA. There should be space left for that. Then we have 2 connectors and the interface card is designed to be as simple as possible, just the retimers and the cages for the transceivers. The implementation of the PME in the FPGA will use the GTH transceivers to create the interface to the optical module. In the receive path, the transceivers will do the analog signal processing, equalization of the signal, because receiving 10G signal is not that easy, and after that, clock data recovery and deserialization into parallel path, which can be processed by the FPGA fabric, by the logic of the FPGA, and the rest will be done in the fabrics, in the logic of the FPGA. The TX is the opposite. Therefore, GTH transceivers will be used to serialize the data and send them with the correct preamp phases and other electrical stuff towards the optical module. The note here says that GTH transceivers are so advanced that they do have complete implementation of 10G Ethernet in them. However, we have to bypass almost everything in those transceivers because 100G is not 10 times 10G. So we will have to do this in our implementation, we will have to bypass all these beautiful blocks within the GTH that are available now. The PCS layer will have to be implemented completely in the logic by us. So we start with encoding of the blocks to the 66-bit blocks. Then there's a 504, the rate compensation, the scrambler, which ensures that the number of ones and zeros in the bit stream is balanced in long-term scale. Then the new module is the alignment marker inserter, which inserts a marker simultaneously to all lanes every 16 kilo blocks, and gearboxes again for the rate compensation of the signal. The receive path is just the opposite. The align block here waits for the alignment markers on all lanes, and just after each lane has received the alignment marker, then we know that the traffic can be sent to the following blocks already aligned, which is good. Then there's a descrambler, 504 rate compensation, and a decoder to the CG-MII interface, which will be provided to the rest of the user logic. The management in 100G remained almost the same. However, several fields in the address space has been added, namely the lane alignment status, the mapping of PCS lanes to physical lanes, because they can be switched, and the interface has to deal with that correctly. So this management is just a little bit bigger than it was, but nothing really new is here. Some preliminary results. Card consumption will be up to 100 watts. Therefore, we will have to power it through a dedicated connector. And one of the reasons why the card is so big, it's full-size PCI, is that we need to have two 50 amps power supplies to get enough current for the FPGA and the other components. Of course, we will need active cooling. Synthesis of the Ethernet IPs, of the Ethernet blocks. For 40G, we get somewhere around 15,000 LUTs, which per port, of course, which means about 4% of the total resources in the FPGA. And 100G is, of course, much bigger. What I didn't mention yet, because it's not the aim of this presentation, is the packet processing at 100G, because at this speed, you can receive around 150 millions of packets per second in each direction. And in the FPGA, where we can't have really high frequency, we need to have a wide parallel path. Probably we will use 512 bits path, which means that within one word we can have the end of one packet, the interframe gap, and the beginning of the next packet within the single word. And we have to deal with that, because if we delay something, we will lose data. We are already preparing applications for this card. The Netcope is our framework for the development of other applications. Netcope takes care of the PCI Express communication because it's always the same. It takes care of the Ethernet communication because every application in our card uses Ethernet communication. The network interface card example is really the simplest possible. It does nothing more than just handles the packet, sends them from the Ethernet to the host RAM and from the host RAM to the Ethernet. HANIC, hardware accelerated network interface card, is on the next slide. It's a little bit smarter than that. After the packet is received, it goes through the filter where we can drop some part of the traffic, whatever it is. And after that, what we do is that we compute hash of several packet header fields, IP addresses, ports, protocol, and so on. And we use 3 bits of this hash to get the number of the DMA channel. And the packets are distributed among these channels and sent to the host RAM into separate queues, separate buffers. Why we do that is because we want to make use of multiple cores or multiple processors in the PC to be able to cope with this amount of traffic. The hash-based distribution ensures that the packets belonging to one flow will always be sent to the same DMA queue. So if the software application wants to observe the whole flow, the whole communication, it has the chance and doesn't need to look into more than one DMA buffer. So this is our plan, what we want to do in the beginning with the card. And that's it. Thank you for attention. I'm sorry.
Started late, but few questions. Somebody question? Okay, go ahead. Mike.
You said earlier in your talk that the frame format hasn't been changed. Does that mean it's still using a 32-bit checksum, CRC?
Yes, the checksum is completely the same.
Okay, so there's no chance of really getting longer packets?
There is no chance of, sorry?
Longer packets than 9,000 bytes?
No, I don't think so.
Okay. Some more questions? No? Okay, thank you, Victor. Thank you again. Next talk would have Pavel Škoda. He is CESNET engineer, but he is also PhD student at Czech Technical University. His focus on laser techniques, and he is specialist on mutually coupled lasers. So, Pavel, the floor is yours.
Thank you. So, ladies and gentlemen, My name is Pavel Škoda, and I would like to talk about our 100G testing, which has been done in 2 weeks last year. And I would like to acknowledge my colleagues Jan Radil, Josef Vojtěch, and Miloslav Hula that were working hard on this with me. So in this 100G topic, I would like to highlight some interoperability issues that we tried to go more into details of those. So my outline is that first of all, I will just briefly go through some used equipment and facilities that we used during the tests. Then I will go or give you a brief overview of modulation formats, as you can see them on optical spectrum analyzer. And then we will go right to the laboratory tests and go through some first initial stage, which were quite short tests, and then interesting transmission tests where we were working on or looking into dispersion compensation and interoperability with coherent modulation. And then I will show some constellation diagrams of coherent modulations. Then we will go to field tests that were carried over our network, GESNET 2. And we have there a kind of multi-vendor environment where we have Cisco DWDM equipment and open DWDM equipment in one network. And then I will conclude my talk. So as for resources, we were glad that we could use the photonic service switching platform, which you can see at the upper left part from Alcatel-Lucent. It has 100G channels, and we have in our network, you can see in the middle part of the equipment in there is Cisco multi-service transfer platform, and the rest is equipped by checklight devices that were developed in GESNET. From the laboratory equipment, I would like to highlight two devices here. First one is the optical complex spectrum analyzer from Apex Technologies. Why I'm talking about him is that his resolution is about 5 megahertz. So you can actually see on those optical spectra more than you could see at a standard telecommunication spectrum analyzers. And then we got also for these tests XFO optical modulation analyzer, so you will be able to see constellation diagrams of optical coherent modulation. Here I tried to just give you a brief overview of some modulations on the optical spectrum. So the thin guy, the second from the right side, is simple continuous wave laser that has a line width smaller than the resolution of optical spectrum analyzer, so you can see just the one line. But when you look at the left side, there is standard 10G on-off keying intensity modulation, non-return to zero, which has classical triangular shape. And you can see there those modulation sidebands, which are equal to baud rate for that modulation. So when you look at just next to it to the right, there is phase modulation, DPSK, differential phase shift keying, that is working on baud rate 40G. And you can also see that those modulation sidebands are a bit further from the center wavelength or center frequency. And finally, on the right-hand side, you see the spectrum of 100G dual polarization quadrat phase shift keying, which is the modulation used by Alcatel-Lucent and will be present in our tests. Here I'll just run through some really simple tests. First of all, we tried, or we took that system and tried how how much attenuation it can sustain without amplification, and we got to number 28 decibels, which that means that if you will just run that system, it can overcome a drop down in power, in intensity, to almost 1,000th of the intensity, and still the coherent detection is that strong that it can decompose the data from the stream and work over that attenuation. Then we looked at the nonlinear effects and some threshold, and you can see actually on this figure that we started from 15 dBm of output power from amplifier that were amplifying the 100G signal. That's the red line at the bottom. And then we increased the output power of the booster amplifier and sent that signal through 100 kilometers of single mode fiber. And here on the picture or figure, you can see that self-phase modulation, which is probably the most important nonlinear effect in this case, spread out the spectrum, and we found that threshold was around 22 dBm of output power from the power booster. That is kind of useful, or that will not hamper the quality of signal. So we found, we verified that the signal is largely resilient thanks to the coherent detection and also thanks to advanced forward error coding. Another test or simple test which we made is a filtration test, because as your network grows bigger and bigger, then you may find in one end-to-end connection more filters in line, like cascaded. So therefore we tried to filter the signal and see how much it can bear actually of the filtering before the connection is lost. So we tried here on the left side to narrow the filter from 100 gigahertz to 30 gigahertz filter. So you can see that the sidebands of the modulation got lost or got suppressed by the filter, but the system was still running. On the right-hand side, we tried to detune the filter from the central wavelength, 40 gigahertz to the right and 40 gigahertz to the left as a maximum value. And if you would tune it more, then the connection would get lost. We also tried in the right bottom figure double filtering, where you can see that the slope of those two filters add up, and the filtering is really hard and narrow. So even for these two filters, the system were running with some increased advanced forward error coding corrections. So finally, to transmission test. Here we tried to verify that 100G system works over dispersion compensated lines. That's issue for our network, because our network is dispersion compensated. It's using on-off keying modulation 10G as a standard. So we were really curious if it will work and if we will be able to find any issue there. So we connected the 100G system through the multiplexer with another 12 10G lambdas and send them out to the experimental network, experimental line rather. And this line was consisted from 6 bands, 100 kilometers long each of them, and we used Alcatel-Lucent amplifiers with space every time, just between two stages of amplifier there is a space for dispersion compensation. So first of all, we tried this dispersion compensation with dispersion compensating fibers that are quite well known and I think widely used. And then we replaced those dispersion compensating fibers by dispersion compensating modules that are utilizing fiber bracket ratings, as you can see on the right bottom figure. And these modules have the advantage in length, because they are really quite short, just a few centimeters or maybe a meter. in respect to the dispersion compensating fiber, which can be even a kilometers long. It depends how much dispersion you need to compensate. So we tried 3 scenarios, one with DCF, one with DCM, and then without compensation. So here you can see optical spectra of that multiplex. You can see there are 12 10G lambdas, and then 2 differently shaped 100G signals that are dual polarization QPSK. So from these 3 scenarios, the 100G was working all the time without any error. So we just wanted to highlight that we would prefer those dispersion compensating modules in our network, as there are some that it has a better performance. It doesn't have that large insertion loss, and also the nonlinearity is lower for DCM. And yes, and that's it. Well, then we found out a nice some kind of interesting feature that the DCF seemed to be more tolerant for precise compensation. So when with DCFs we would we didn't have to compensate the dispersion so precisely, and the system worked, let's say, same like if you would compensate it precisely with DCM. But the modules with fiber break ratings have the advantage that they are usually tunable, so you can tune it quite precisely and set it up according to your wishes. So as a result, we verified that 100G system or coherent system work over both compensated and uncompensated line, which was in our case 600 kilometers. So we wouldn't hesitate to put it right into the production line. So one more test which we done actually as the last one in laboratory was the interference test, where we see some kind of strange behavior, because we just changed, we used the same setup, but we changed the frequency plan or the lambda plan. We set there 14 lambda channels, 10G each of them, and then we slipped on the 50 gigahertz. Okay, those 10G lambdas are on 100 gigahertz spacing, and those 2 100G channels are on a 50 gigahertz spacing, slipped between those 10G. So in a bottom picture or figure, you can see that we measured 1,000 million corrections of advanced forward error coding over 15 minutes of run for this guy. And once we pull out those 3 10G lambdas, which were around the 100G channels, we observed even bigger corrections, which goes a bit against the common sense. But we tried to address it, and we believe that it's because of power balance of the complete system, as those amplifiers were working in a power constant regime. So as you pull out some channels from the line, the amplification gets bigger on other channels, and also the amplifiers will work in a different regime, and they may have some other phase noise than before, so it could add to the coherent signal then. So there was actually some mutual influence, and we would like to test it once again once we will have 100G system available. So constellation diagrams, I hope they are a bit visible here. Well, we got these guys thanks to PSO 200 from Expo, and we found it quite interesting because it's not so easy to analyze a 100G system, well, the signal itself, because there are no, let's say, universal analyzers. So here you can see the analysis of dual polarization quadrature phase shift keying, which is the 100G modulation used by Alcatel-Lucent. And the signal or the data are transferred in two polarizations, orthogonally one to each other. So we can see one polarization in the upper part and the other in the lower part. And each of these polarizations have quadrature phase shift keying modulation that is represented on complex plane by 4 points in complex plane. And then you can see also the eye diagram of eye in phase and quadrature part of the signal or of the modulation. So this picture you will get when you will connect the modulation analyzer just after the system, just after the transceiver of 100G. If you will put there some 10 kilometers of fiber and add there some dispersion compensation, you will receive almost the same picture. But once you will prolong it to 100 kilometers, the transmission line, and put there some amplifiers to overcome such a distance, then and also put there some dispersion compensation, then you will see that the picture will get blurred, and you will and this is done by the spontaneous emission from amplifiers, the noise from amplifiers. And if you would leave there some residual dispersion, you will see that the constellation diagram will get twisted, and you may not recognize even the modulation points on a complex plane. So this is this is one of the options how you can judge on a signal quality. And I would like to highlight just some features that actually this equipment do not actually retrieve any data, as every vendor has usually some specific or vendor-specific forward error coding mechanism, and they also usually differ it from platform to platform. So such a device would have to know all the FEC mechanism and have them implemented to actually retrieve the data. So we could see only the modulation itself, not the data from it. So the only way how we could judge on the performance of the system was from a FEC the number which we retrieved from the box themselves about the performance. It's some statistical value which is gathered every 15 minutes. So that's why we have there those corrections per 15 minutes. So then we set it up for field tests. So in our network there are two, let's say, two sets of equipment used. The blue lines you see there is a Cisco, and then the red lines we have our own system from Checklight family, and it was designed in GESNET. So in these tests we tried to work in a multi-vendor environment, so across two different systems, and then we used also single fiber bidirectional transmission lines, which are in the northwest of our country. And we also have a non-standard photonic service in operation between Prague, the capital city, Brno, and Austria, that is south from Czech Republic. So in details, first of all, we have made a loop that was 778 kilometers long, and we had their photonic service in operation in the same fiber, just in a different wavelength, and it was over the distance of 300 kilometers. And in this case, we got a number of performance of the system with corrected errors by the advanced forward error coding 4 times 10 to 9. In the next test, we prolonged the length to 1,000 kilometers, and in this case, we received another number of corrected errors, but the system was working all the time, and we didn't receive any impact on that photonic service, which is quite precise. It's an atomic clock comparison service, which is, let's say, non-standard in data transfer. So we also try to measure the constellation diagram for the shorter loop, for that 778 kilometers. And we end up in quite a nice figure where we got also a lot of noise from amplifiers, but as you can see, the dispersion was compensated quite precisely, and you could actually see where the constellation diagram points, modulation points, are on a complex plane. So another two tests which we carried out, it was a loop from Prague, again to Prague, but across the multi-vendor environment. So it means both Open DWDM and Cisco DWDM. And in this case, we overcame 4 spans at 22 dB attenuation, and another 4 that had even more, 30 to 34 dB of attenuation, which is quite a lot, and we believe that it's a cause of the bad performance of the system and also some uncorrected errors in a system. There were also the photonic services running along. And the very last one test was across the single fiber lines, and actually the loop was 655 kilometers long, and more than half of it was single fiber lines. There were 3 critical spans of 35 decibels, and the line was working with also some corrected errors, as always. So to conclude this, we would like to highlight that ALU 100G, Alcatel-Lucent 100G coherent system is working over compensated networks. So we don't have any worries about deploying it in our network where we have the compensation, dispersion compensation. We would recommend to use fiber bragg ratings rather than dispersion compensation fiber, because dispersion compensation fiber has a higher insertion loss, nonlinear effects, and some additional delays because of the length of the fiber. So we also verified that Alcatel-Lucent system works over a multi-vendor environment, the Cisco and Checklight in our case, and it is possible over single fiber lines. We had that 100G's coherent system there as a line wave through our system. Well, I would like just to acknowledge Martin Lorenz from Alcatel-Lucent and Vladislav Blažek and Artur Mohr from Exfo for provision of devices, and also Martin Michal and Vašek Novák for their big help with experiments over our Cisco production network. And this research was also received some funding from European Community, from GESNET. And the last thing which I want to do is to invite you for a 7th Customer Empower Fiber Networks workshop, which will be held in Prague in September. And it's mainly focused on national research and education networks, but even people from production or from vendors and so on are welcomed, and we will be dealing there with some interesting things around the national research and education networks and their needs and requests. So I just list up some interesting points here, and you can see also the links to the previous years. So I thank you for your attention.
I'm not how many people understand it well, so not me. So I'm not optical specialist. So, but please open floor room for the discussion. Question, okay?
You mentioned one of the slides that the nonlinear threshold is 22 dBm.
Yeah. Well, yes, that was threshold for in our measurement for 100 kilometers long span. So actually we went a lot of below this number, but we found it as a threshold for 100 kilometers of standard telecommunication G652 fiber. Oh well, we define it here for our purpose for that 100 kilometers long fiber, and in this case we observed some errors in the system in a line. Let's say there were some the line was broken just after this threshold, thanks to self-wave modulation in there. Yes.
More question? Okay, no
Yeah.
problem. We have the time.
Well, those amplifiers were set up to increase the power to 16 dBm as output power for the whole multiplex of those channels. So I actually don't know exact number now, but there were those 12 and 2, so 14 channels which are amplified to 16 dBm of total power.
Okay, so more question? No? Okay, thank you, Pavel, once again. Next talk would be from Dr. Jeroen Kolemij from the Laser Laboratory of University of Amsterdam. He is physicist. He is a specialist on the exact time and frequency measurement, as I understood. He worked even on the several projects in US on the development of the most exact clocks on the world, I think. Okay,
That's right.
so Jeroen.
Well, first of all, let me thank the organization for giving me the opportunity to talk about this subject. And while the talk is coming up, let me say that I think that I'm in the wrong session here. We've been hearing talks about 100 gigabit per second connections, and now we're talking about a laser that requires less than 1 hertz of bandwidth to be transported. Just a second here. Do you think the problem will be fixed? Oh dear. Coffee in the meantime, but it seems it will be solved in 20 seconds from now. It's it's the PowerPoint one. There we go. All right. So what I will be talking about is partly about atomic clocks and the role that they play in network synchronization. Atomic clocks are maybe best known for defining the International Atomic Time, and in relation to that, Coordinated Universal Time, UTC. They're also used as Stratum 1 frequency references in telecom networks. A very important role they play is in the Global Positioning System, GPS, in which each GPS satellite is equipped with a couple of atomic clocks. And that is actually it's the accuracy of the clocks that make GPS work and then also enable the positioning. and atomic clocks are used in scientific applications. But I think the network synchronization part is the most important part for our society. Things like power grids and even electronic financial transactions, they can't do without atomic clocks and in particular networks of synchronized atomic clocks. So in my talk I will briefly review the principle of operation of atomic clocks and discuss the state of the art in atomic clocks and timekeeping. And then I will move on to optical time and frequency transfer, which might be done through optical networks, and I will also discuss a couple of applications. So any atomic clock basically consists of three elements. One is you need a very stable oscillator, for instance a microwave source, that you reference to the oscillations inside an atom. You can find atoms that have very pure and very accurate oscillations, and you can use those microwaves, for instance, to set the atoms in oscillation, and you just build a servo loop to keep your oscillator frequency fixed to the atomic reference frequency. And the only thing you need to have then is a counter that converts the oscillations of the oscillator to some useful quantity. Now, today, the definition of time, the second, is based on cesium atoms, and cesium atomic clocks are based on microwaves indeed, and the accuracy that you can get is about 15 to 16 significant digits. Now, since about 10 years or so, there's a new generation of atomic clocks, which are so-called optical atomic clocks, and they are based on lasers. In that case, the oscillator is an ultra-stable laser which has an astonishingly small line width of less than 1 hertz. And what you do, you take a special device which is called an ion trap, in which you can trap single atoms. This is a picture here on the right of 4 individual atoms that are trapped. You can even trap a single atom, and if you take a suitable atom with a very pure reference oscillation frequency inside, you can actually drive the oscillations in the atom with the ultra-stable laser, and this is the basis of your clock. And the only thing you need to do then is somehow count the optical frequency of the laser, which is done using a so-called optical frequency comb, which is almost literally a ruler in frequency space, which you can use to read off the frequency of your clock laser. Now, the most accurate clock that was built, and I was so fortunate to be part of that team in the United States, is the so-called aluminum ion clock, which now has an accuracy of more than 17 digits. And just to give you an idea of how accurate that is, these clocks are accurate enough to sense relativistic effects from the theory of relativity of Einstein on the human scale. So if you would take this clock, you would be walking with 2 meters per second, the clock would sense a significant delay in time, or dilatation as it is called. Or, and this is an experiment that my colleagues did at NIST, they took 2 of those aluminum clocks and they lifted up one by 10 centimeters, and that one started ticking faster, noticeably. And it's the same story as the science fiction story where you take a clock, you throw it into a black hole in space, and time just stops in the black hole because of the infinitely high gravitational potential. It's the similar effect that causes these clocks to be ticking at different speeds when you place them at different heights. So optical clocks are not only time-keeping devices, but they've also become what I call Einstein sensors of these funny relativistic effects. There's more scientific value to these optical clocks, because the clock frequency depends on the structure of the atom, the way the electrons are arranged around the nucleus, and it also depends on the value of fundamental constants. For instance, there is the so-called fine structure constant alpha, which is made up from other constants like the electron charge, the speed of light, and we call them fundamental constants of nature, but actually that's just an empirical fact. We haven't seen them change over time, so that's why they are assumed to be constant. We also don't have very specific reasons to believe why they should be changing, although there are some new theories that actually allow for these constants to be changing over time. So if you take 2 atomic clocks based on different elements, then the clock frequencies, they depend differently on, for instance, the fine structure constant. So if the fine structure constant value is changing over time, these two clocks would start ticking at different rates. And there has been a test to test whether the fine structure constant is changing. My colleagues at the National Institute of Standards and Technology, they not only have an aluminum optical clock, but they also have a mercury optical clock. And they have a totally different dependence on the value of the fine structure constant. And by comparing these two clocks over the course of about 1 year, they could establish that the fine structure constant is actually indeed constant to within 2 parts in 10 to the 17, which is the most tight constraint on the time variation of alpha. Now in Europe, there's also a number of laboratories that have optical clocks, but almost none of them is in the luxurious position as my colleagues at NIST, where they have 2 optical clocks. In Europe, you have optical clocks that are separated by at least 100 kilometers. Each lab has 1 clock. And if you would like to compare them, you have a problem. For instance, in the Netherlands, we are building up an aluminum ion optical clock in Amsterdam, and in Groningen, they are building a radium optical clock, and we could do a similar test as my colleagues at NIST. But we have to compare these clocks across this, over this 150 kilometer distance. So how to do this? Well, normally if you want to synchronize clocks, or if you want to compare clocks, you could use GPS. That's the best way, the best method that you can get. And that works well for these traditional atomic clocks, like cesium clocks, but it's not enough for these optical clocks. And just to illustrate this, this is a picture of the development of the accuracy of clocks over time. So the first atomic clocks were developed in the 1950s, and now something went wrong here. But so currently we have these optical atomic clocks that have 17 digits of accuracy, whereas GPS, as a time transfer mechanism, can give you at most 14 to 15 digits of accuracy. So if we want to compare optical clocks, then the question is how to do this. And one way might be to improve GPS. You might wonder, isn't that possible then? No, the accuracy that GPS can provide you is strongly limited primarily by atmospheric disturbances. These satellites are flying around the Earth at 20,000 kilometers height, and their signals have to propagate all the way through the atmosphere, and there's just some uncontrolled disturbances that limit the accuracy there. So you have to come up with a different way. And it has been mentioned, I think already, also in the previous talk, you can use optical fibers for this, perhaps. After all, the ticking signal of an optical clock is a laser, so why not use an optical fiber for time and frequency transfer? So now there is a problem, because these optical clocks, this ultra-stable laser normally is in the visible wavelength range, or even in the ultraviolet wavelength range, so nothing that you could send into an optical fiber for telecom. But this frequency comb laser that you use to read out the clock frequency, and just to illustrate how that works, so this frequency comb laser is a laser that's is not lasing at one mode, but at many CW modes at the same time. So you literally have a comb of very evenly spaced optical modes, and you can simply count the number of modes until you reach your clock laser frequency. And you can measure actually the spacing between the modes, and you simply multiply the mode number of your clock laser with the spacing to read off the optical frequency. But there's another thing that you can do with these frequency comb lasers. You can take your clock laser and phase lock it with a servo loop. You can phase lock it, or you can phase lock the mode of the comb that's closest to the clock laser, to your clock laser. So unfortunately, I don't have a laser pointer here, but you can actually force this particular mode to become phase coherent with this ultra-stable laser. And the nice thing that happens then is that all the modes of your frequency comb laser, they inherit the same phase stability, including the telecom wavelengths near 1.5 microns. So you can simply take those modes from your frequency comb, you can extract them and send those into an optical fiber to transmit to other locations. So you could think of a way to compare optical clocks in different places with an arrangement like this. Like I said, you send it into an optical fiber, you send it to a remote lab, and there you couple it out and you compare it with a second frequency comb laser that's referenced to your second optical clock. But something that is a question mark here is what about the optical path length fluctuations that occur in such an optical fiber? Things like acoustic disturbances or thermal fluctuations. So in the Netherlands, we started collaborating with SurfNet, and SurfNet provided us a link, a DWDM channel running from our lab in Amsterdam at the VU University all the way to KVI in Groningen. So we have an arrangement like as illustrated above. So both in Amsterdam and in Groningen we have frequency comb lasers, and in Amsterdam we have our clock laser, and we send it into a DWDM wavelength channel provided by SurfNet. It's a 317 kilometer long link to Groningen, and we actually have a round trip. We also sent the light back to Amsterdam, and it's a fiber that's also carrying other live data traffic at the same time. So the first test that we did is the following. We have our clock laser in Amsterdam, we have our frequency comb laser, we send the light through the optical fiber like I just discussed before, and to check whether how accurate our measurement is, we also establish a GPS link between the two labs. We use GPS to compare the two clocks in a second way. So we have two ways of comparing the clocks. And what we can do then is we take our optical frequency measurement, our optical frequency comparison, and we can make a so-called Allen deviation plot. Because the longer you measure an oscillation, the longer you average, the higher the accuracy or the stability of your measurement will be. And that's indicated in the plot here. And what we see is that the stability of the frequency comparison through the optical fiber goes below the 3 × 10⁻12 accuracy. That's a fractional accuracy. And then it starts sort of leveling off. And this red dashed line indicates the accuracy of the GPS system. So we see that our optical clock comparison goes just below the GPS specification and then starts leveling off. And we can't really tell whether it's GPS that's limiting us or whether it's the optical fiber. But at least it's as good as GPS. Well, can we say more, perhaps? Well, this is why we did a second test, where we actually make a round trip. So we go through one fiber to Groningen, and we go all the way back through a second fiber, and the input and the output of the fiber are side by side on an optical table, and we can simply compare the two. We can compare the light that was sent in with the light that came back, and then we are independent from a GPS measurement. And then we can plot again an Allen deviation plot, as illustrated here. And what you see is that after some 5 hours of measurement, the stability of the link turns out to be a few times 10⁻15. And that's performance that's better than state-of-the-art GPS methods. So it shows that with a relatively simple arrangement, like we have in the Netherlands, you can have time transfer better than the state-of-the-art GPS. And the limiting factor here is likely the optical path length fluctuations in the fiber. Now, okay, so we have established that we can achieve 14 to 15 digits of accuracy through optical fiber, but these optical clocks are still 2 orders of magnitude more accurate. We require 17 or more digits of accuracy. And there's a solution to that. That's called active fiber length compensation. It was it's a trick that works as follows. So you start out with a very ultra-stable clock laser, which has a frequency spectrum that's just absolutely stable, no noise at all. And then you send it through an optical fiber, and because of the optical path length variations in the fiber, you will add some phase and frequency noise to your laser. So the laser is jittering as it comes out of the fiber. Now, there's a trick that was developed by in the group of Jan Hall, who was the 2005 Nobel Prize winner. Actually, he was one of the co-inventors of the frequency comb. And what they realized is that if you place a mirror at the end of the fiber that sends part of the light back through the fiber, then what comes back at the entrance contains 2 times the noise. The light goes back and forth in a very short time. On that time scale, the path length of the fiber doesn't really change, and you can actually measure the instantaneous path length. And with this knowledge, you can build a noise detection and noise compensation system so that you can pre-compensate the frequency of your clock laser as it goes in, and what comes out is just as stable as the light that you send in. And without going into much technical detail here, let me just summarize what is possible using this technique. It works, for instance, in installed urban dark telecom fiber. My colleagues in France, in the USA, and also in Germany, they've shown that you can go even to 900 kilometers of fiber links and achieve, with this compensation, you can achieve 19 digits of frequency transfer accuracy. It even works in live telecom networks where they use one dedicated DWDM channel to do this compensation trick, and at the other channels you have live internet data traffic running, and they still achieve 19 digits of accuracy. And you can also daisy chain segments of about 100 kilometers long. So you can really cross large distances using this technology. And until now I was talking about optical carriers, very stable optical carriers, but you can also modulate an optical carrier with, let's say, 1 gigahertz or so, and use the gigahertz as your clock carrying signal, which is easier to detect. And this also works thanks to this compensation method, and you can achieve about 18 digits of accuracy. And just to mention again, this is really orders of magnitude more accurate than you can achieve through GPS, which is the current state of the art. So I think this demonstrates that this really is the technology for the next decades. There's already quite some activity in Europe in this research field. Recently, there was a project started within the European Metrology Research Program, which aims to connect all the metrology institutes in Europe through optical fibers, using length compensated fibers and so on. And part of this this link will be running through the Netherlands. I don't know if you recognize the Netherlands in this picture, but it's up there in the northwest, so to say, and it has a small green segment running through it. And that's the link that I discussed previously between Amsterdam and Groningen. Now, there's a general issue that all the labs and also this consortium is facing, because getting access to fiber, to dark wavelength channels, and it's even harder to get access to dark fiber, is difficult, or it's expensive if you have to talk to a commercial fiber owner. So if there's anyone in the audience that has an idea of an infrastructure that would be available for this kind of technology tests, I'd be happy to discuss that later on. So I discussed already some scientific applications. There's also something you could do with these clocks called relativistic geodesy. You know that the Earth is not a perfect ellipsoid, but it's more like a potato, and the surface of this potato is called the geoid. It's the equipotential surface, you may call it sea level if you like, which corresponds to an equipotential surface of the gravitational potential. Now, clocks are sensitive to that. They are sensitive to gravitational potential, whereas GPS measures height with respect to some imaginary ellipsoid, this idealized shape of the Earth, and then GPS converts the height with respect to the ellipsoid, it converts it to the height in the frame of the geoid, but this frame transformation that is involved in this introduces some inaccuracy. So the height through GPS cannot be measured with an accuracy better than 2 to 3 centimeters or so. Whereas these clocks, these optical clocks, at the end of this decade, they are expected to achieve an accuracy so that they can send 1 centimeter height differences or even less. So you could use clocks to improve the model of the Earth, or to improve the transformation between the GPS frame to the real geoid frame. And that might be interesting for searches for gold or mineral reserves. Often people use gravimeters to search for cavities or places in the Earth crust where there's a density variation because there's oil or gas in there. And these gravimeters, they basically measure little g, the gravitational acceleration, which scales with 1 over r squared, with r being the distance to the center of the Earth. And therefore they are sensitive to density variations right below our feet in the Earth crust, but they're also sensitive to height variations. And they actually cannot distinguish between a density variation or a height variation that happens unnoticed. And here you're limited by this GPS data with this inaccuracy of about 2 to 3 centimeters. Now, if you would use fiber-coupled optical clocks to measure the gravitational potential, you would basically be measuring the height so that you can separate out the height variation. You can separate out the height variation from the density variation, and you can actually improve the sensitivity of these gravimeters to density variations, and you can be more sensitive to searches for gas and oil and so on. Then there's another thing. If you have accurate time and frequency available everywhere in your optical network, you can do whatever GPS can do. And because these clocks are much more accurate, you can even do better. So you can think, first of all, of a timing backup. Everything, any technology that's now depending on GPS, for instance, the electricity grids, you could build a timing backup so that in case that GPS fails because of a solar storm or what have you, you have a timing backup system so that your system will survive the GPS outage. And you can even think of next generation network synchronization. So just to illustrate how accurate this super GPS could be, it's illustrated in the same plot that I've shown before. It's expected that it will be able to achieve some 19 digits of accuracy somewhere in the course of, 2020, 2030 or so. And then you can think about enhanced terrestrial positioning systems. So you can achieve very high accuracy positioning even indoors and on busy highways. For instance, using the signals that are broadcast by the antenna masts for mobile telecommunication, which you indeed can receive indoors. And if I talk about high accuracy, I'm talking about on the order of 10 centimeters of positioning accuracy. Another interesting thing is you might actually verify the timing in the experiment between CERN and the lab in Gran Sasso, I should say, where they observed, or where they thought they observed, superluminal neutrinos. If you do an experiment like that, you have to synchronize the two clocks in the two labs that are separated by many hundreds of kilometers. And now they were using the GPS system because there's nothing else available. But if you have an optical fiber link available between the two labs, you could do much more accurate synchronization of these two experiments through optical fiber. You could use these Einstein sensors for relativistic geodesy. In the Netherlands, we have the situation that a large part of the country is actually below sea level, so we are very much depending on the embankments and the dikes that protect us. And we need to have a close watch on whether these dikes are slowly sagging or not, and these clocks could be used for that. And there's many other applications that we cannot even think of, I think, that will be possible through this technology. So this almost concludes my talk. I would like to thank in particular Roland Nuits here in the audience from SurfNet, who has collaborated with us and has made a lot of things possible between our labs in Amsterdam and in Groningen. And I'd like to thank my colleagues from Amsterdam and from Groningen, and I'd like to thank you for your attention.
So we have time for questions. No?
No one wonders how you make a 1 Hertz line width laser?
We are doing the similar things in the GESNET, but our colleague is Smotlacha is not here, so. Otherwise, we definitely should have, because he had a talk on the previous Terna conference about a similar project, how he did the measurement between the Prague and Vienna in the same way.
Yes. Well, please send my regards to Vladimir.
Okay. So, no question? Okay, so thank you again. I would like to thank all of you for visiting this session. So it's very good. We had about 80 people here all the time.